So next, we've got Sue Keay, CEO of the Queensland Hub. It's really exciting to see Sue here today. She will be presenting a paper on future applications of cyber physical systems to mining. I had the pleasure of working with Sue and supporting some of her very visionary work when she was actually developing the first robotic vision research center at QUT. Sue went on to work at Data 61, and last year she actually published that first robotic roadmap that I was actually talking about. She has a PhD in geoscience and an MBA. Sue combines science with business. She has interest in entrepreneurship and disruptive technologies and studied QUT's social robotic program. Sue serves on the board of the CRC for optimizing resource extraction and the expert advisory panel of Queensland AI. So it's a pleasure to have Sue here today. Sue, over to you.
Thanks very much, Rick. So I'm going to be focusing a bit on some work that predates my time as CEO of the Queensland AI Hub. I've been CEO now for 3 months, but before that I was the research director for cyber physical systems with CSIRO's Data 61. And just to set the scene and describe what I mean by cyber physical systems, it really is around robotics and artificial intelligence. So having a look at how we can apply robotics, AI, Internet of Things, and even combine that with the biological in the form of cybernetics to solve challenges around us. As Rick mentioned, I was, involved in putting together Australia's first robotics roadmap. As part of doing that, we tried to have a bit of a look at what the current capability in Australia was in the robotics space. And at the time, there hadn't really been previous attempts to map this out. And to, our best attempts at putting this together, we discovered that there are more than 1,000 companies across Australia, and those are all represented by those little red dots you see on the continent, that have some capability in robotics. That doesn't mean that they are robotics companies, but they might be companies that have a section that specialises in robotics or automation. As you can see, we used very broad terms because we also wanted to capture people who were developing computer vision systems and sensing systems. But it really shows that there is a lot of capability here in Australia, and although it is still a fairly fragmented and immature industry, I believe that there is quite a high degree of potential for Australia in this area, and I guess that's really what I'd like to see us pursuing. And, just to get everyone, behind the idea, this is a reminder, these are automated straddle carriers that were first developed here in Australia. This is a video of the port of Brisbane, which was the first port in the world to be automated. These automated straddle carriers go around the port, picking up shipping containers, putting them on the back of trucks. There are no people on the ground when these automated straddle carriers are operating. They are all in a control centre watching what is going on. And, it's a similar story with our mine sites, being the first country in the world to really automate a lot of our mine sites. And I really think we need to be making more of the opportunities we have in developing some of these world firsts. Now, there are a lot of different uses of robots in mining, and, these are just some of them. I think it would be fair to say that a lot of the applications are really still focused on surface mining, less so in more difficult to get to areas underground or underwater. But you'd probably all be familiar with some of the current uses of things like robots. But I think it's where the potential uses of robots in mining are at that it starts to get interesting. I think you're going to be seeing greater use underground. If we can see more application in mineral processing, in particular, if we can start to look at the scale issues and what we can do with much smaller robots, I think that would adds a lot of potential. There are clear benefits of applying robotics to health and safety and even just to general logistics. But there are a number of other things where we can help to navigate in GPS denied environments, developing robust heat and pressure resistant robots that can go to more places than our current stable of robots can go, and even moving into the realm of being able to 3D print a lot of mine infrastructure and mine maintenance equipment, which then leads us to where we would hope to be in terms of space robotics, how we can build robots that can operate truly autonomously to explore and mine in space. And to do that, we need to be heading towards the development of self-repairing and even self-building robots. So I think there's an exciting future in terms of how we can apply these technologies in the future. Now, just to give you a bit of an idea of what this means, this is terminology that's probably usually only of interest to people in robotics, but in general in the world we divide robots up into industrial robots versus service robots, and it's just interesting to see some of the trends because we do collect data, or at least the International Federation of Robotics collects a lot of data on the trends that are happening in these areas. The industrial robots are the robots that you would typically find on the manufacturing factory floor, like the one pictured there on the left, whereas the robots that you would typically find on a mine site would be called service robots, so things like your autonomous haulage vehicles. And as you can see, in industrial robots, we're seeing quite a contraction in the market, but the market for service robots just continues to expand at an enormously high rate. And what I guess the message I'd like for people to start taking away is it's a pity that Australia is not taking more advantage of our strengths in this area to take advantage of this booming market. In terms of field robots, which are a class of service robots which most mining robots fall into, you can see that field robots are one of the top 4 applications of service robots. So nowhere near as many field robots as there are medical or logistics robots or even robots in defence. But, you know, it is a steadily growing market and one that's super important to Australia. In terms of field robot sales in Asia, Australia, in the last year, there were only 393 total units sold, but you might appreciate that's because some of these are very big robots. And when I talk about field robots, that includes not just mining robots. So that's not 393 robots applied to mining, that's also applied to agriculture, milking, space, and, it'd be interesting to think about what the other category is, but things that they couldn't put into those other 4 categories. Sadly, most field robots are produced in Europe and the US. Just 4% are coming from our local area. And that is a statistic that I would dearly love to see changed. And one of the challenges that we still face is that robots are not commonly applied in unstructured environments, which is really where certainly a lot of our exploration is taking place. And that is gradually changing, though, as we are able to access greater computer processing power and really harness the power of computer vision to collect information that enables our autonomous systems to operate in unstructured environments. And yeah, so as I mentioned, one of the things that's really making a big change in how we're able to apply cyber-physical systems in general is that integration with computer vision. So you can now put cameras on just about anything and put them in quite dangerous situations and get that autonomous system to operate without without the necessity for people to be involved. And that, is, I think people forget that how far we've come in such a short period of time, because it wasn't that long ago that people would never use cameras on something like a robot to help it navigate because it just wouldn't be safe. Because by the time you were able to process all of the information from the camera and determine a path forward, the path could very well have changed, which is why for a long, long time, and as we still should rely on LiDARs to be able to get a good geometric sense of the surroundings. And, LiDAR technology is never going to go away. We always need to have combinations to make sure they're safe. But really, computer vision is adding a whole new dimension and a whole new aspect to what we can expect these systems to be able to do in the future. And something that has had a huge impact on the development of these systems is what we call deep learning. And that's really just a way of describing machine learning that, mimics in, a very rudimentary way, the way the humans think. So rather than, you know, having to write lines and lines of code to get robots to learn what they need to do, it's about training robots by showing them what to do. As you can see in this image where someone is showing the robot a ball and is going to be teaching them what it needs to be doing with that ball. So we're getting to the point now where robots can learn like many of our children do by watching YouTube videos. And why that's important is because if we can train unlike humans, if we can train one robot up to do something particularly well, then essentially you can train all robots, because that information can just be transferred seamlessly to all other like robots, as you can see in this video of all these robots doing the same thing. And if you can do that, then why that's important is that it means that you can achieve scale. And scale is what we require if we're really going to solve some very big challenges that are facing us at the moment. And this is an example that I love to give about how robots are being applied to solve environmental challenges, such as protecting the Great Barrier Reef. So this underwater robot called RangerBot, developed at QUT, uses computer vision to navigate its way around the reef, and it can serve a range of functions. It can help to control the number of crown of thorns starfish. It can also just be used to survey the health of the reef, but it can also be used for tasks such as collecting coral spawn and moving it into waters where the temperature is more suited to coral development. So it can be used not just for protection, but for remediation of the environment. And I think, you know, when we're thinking about these technologies, I'd like everyone to keep in mind what are some of the grand challenges that we as humans can't easily solve, that if we were able to apply enough robots and scale to solve, you know, what are those things that we could be, what are those problems that we could be tackling and looking at solving? And there are a multitude. And one of the trends that we're seeing in terms of the development of these technologies is, you know, the application of artificial intelligence, specifically machine learning, to just about everything, in particular in terms of what these systems look like. So when I was with CSIRO's Data 61, this was the headline in a Wired magazine article about the work from some of our researchers, which, as they describe here, were the scientists who were helping robots evolve weirdness in shoes. And that's because to develop different robotic components, the researchers were using machine learning at every different stage of development. So first, they'd be using machine learning to determine what material to construct the robot out of, because again, thanks to machine learning, we are inventing new materials at such a accelerated rate that it's impossible for a human to keep on top of all of the different types of materials and their properties to be able to really determine what is the best property for any particular application. So first, the researchers were using machine learning to select the material with which they would make a robot component. And then they were using machine learning to look at the shape or morphology of that component and what it should best look like to do the job that it required. So that strange yellow and green figure on the right is a robotic leg that was specifically developed to be good at walking through water. And then finally, the researchers were applying machine learning to help to actually get that component to figure out what its job was. So in this case, with these robotic legs pictured, the robot would be set up in a sort of circular track to figure out how to move around, you know, with no training given to it at all. So what's the trend that we're seeing here is about expanding the creativity that we as humans can access. So once we were limited just by our imaginations or the type of designs that we saw in animals to look at how we might build robots. But now we have this whole new paradigm that, you know, we can call on, where we can use machine learning to come up with designs and materials that we perhaps never would have dreamed of. And that opens up a whole new range of possibilities. The other trend that I think is going to have an impact in all sectors, but mining included, perhaps mainly in the logistics or sort of back of house space, and that's what I like to call the roboticization of commodity products. So what this video is showing is just an everyday trolley that has been turned into a robot by adding some robotic wheels. And I think that increasingly in the future, what we will see is not so much building robots up completely from scratch to serve a particular purpose, but actually changing products that we have all around us and converting them into robots. Because there's such a long product cycle associated with developing a new robot that if you can just convert something that already exists into a robot, then you're really saving a huge amount of development time. And that's why, for example, with self-driving cars, we're not seeing people at this stage completely reinventing the car, because it's very convenient to use that 100 years of design and manufacturing knowledge to build something that you know is robust and reliable, and then just making it into a robot. Now, I wanted to talk, I suppose, reminisce a bit about some work that was done at CSIRO's Data 61 while I was still there and is ongoing, and that is about Australia's participation in the DARPA Subterranean Challenge, because I think that everyone would be able to see a lot of the applications to the mining industry. And seeing part of Adrian's talk, I noticed that there are some images from Emerson, which will also feature in this description of DARPA. But for those of you who aren't familiar with the DARPA challenges, these are grand challenges that are funded by DARPA and open to teams from all around the world, and really are aimed at pushing forward the limits of our current technologies so that they can be doing things that haven't been possible in the past. So it builds off some very successful challenges in the past, one of which was the DARPA Urban Challenge back in 2008, which actually led to the whole development of the self-driving car industry. With the Subterranean Challenge, CSIRO's Data 61 team, in conjunction with Emerson and Georgia Tech, were the only non-US team funded by DARPA to compete, which just again reinforces the fantastic capability that we have in cyber physical systems here in Australia. And the purpose of the Subterranean Challenge is to get robots to operate underground with limited communications, completely without any help from people. And the application that they are thinking about is a rescue scenario. So being able to get real-time situational awareness back to the surface, so someone can make a decision whether it's safe to send people down into that situation. And this is exactly the sort of scenario that robots should be good at, and that we should expect robots to be able to send robots down into. But as we found when the Fukushima nuclear meltdown happened, unfortunately, despite many years of research into the field of rescue robotics, we're still not quite at the stage where we can rely on these systems to go and do things. But that is starting to change. So, I mean, I guess where we're heading with this is that we need to be able to develop strategic, tactical and adaptive path planning and machine control, object detection and classification systems to ensure that we can optimize collision-free navigation. And that is still a work in progress, but we're really starting to get here. And I guess what's pictured here are some of the different platforms, because the other aspect of the Subterranean Challenge is using a team of robots that have to work together to be able to achieve their goals. So this was the first competition. There are a couple of stages in the competition. The first one was an underground challenge that was held in an underground mine, which was an experimental mine in Pittsburgh. The second challenge was one that was held in an abandoned nuclear facility in Washington State. So it was an underground urban environment. And the final challenge, which the team has just recently undertaken up at Chillagoe, because they can't travel to the US at the moment, was around having this robot team navigate it in a natural underground environment, i.e. a cave system. So this was the team in action in the first challenge. The team came fifth in this challenge, But they really did the best job in terms of all of the teams that were competing from all around the world in being able to share maps between the different robots that were entering the course. The more robots that you can reliably control and put into the course, the more distance you can cover and the more likelihood that you're going to be able to find artifacts, which is how you are judged in the DARPA challenge. So the team has to find a red backpack, a mobile phone, a pretend human, and also be able to detect a gas leak, and all of those things, and being able to accurately position where those things are located go towards giving points to the teams, and on that basis DARPA selects which team were the winners. This highlights not just the Data 61 team's robots. This is a little clip of all of the robots from different teams that were operating in the second challenge. You can see that's one of Boston's Spot robots. Many of the teams were starting to experiment with drones. That's the Emerson drone going down a shaft. Many of the teams were experimenting with how you could launch drones directly off the back of the ground robots. You can see this is just showing what the course does, the different types of artifacts that the team of robots had to be able to identify. And yes, this is a quick description of the cave circuit, which we've had to, or the CSIRO's Data 61 team has had to try and replicate up at Chillagoe in Queensland. So this is just an image of the team that went over and were competing in the second challenge and the robots that accompanied them. As you can see, it's a combination of tracked robots, also carrying the Emerson drones on the back and using a Australian-developed system of navigation called Wildcat. This is the system overview, so it consists of a range of different sensors, cameras, thermal LiDAR, inertial measurement units that are all combined and put onto each of the robots, including the drones, and this information is able to be shared across all of the robots. So as I said, you can have robots operating in different areas, all sharing that information and making sure that the robots aren't retracing steps that have been taken by one of their teammates. This is the Emerson drone launching autonomously from one of the tracked robots while it was on the course. Because communications was deliberately difficult, and you can imagine in an abandoned nuclear facility, you're surrounded by concrete walls up to 3 meters thick, so very difficult to get good comms. And so the team actually took comms nodes in, and one of the jobs of those big orange Titan robots was to drop those nodes as they went into the course so that the robots could communicate with one another and also communicate with the sole operator up on the surface, whose role was to actually mark off artifacts when they believed that the robots had been able to discover them. And this is an image, a short video of the team actually in action. So it's going to be fuzzy in places because this is footage taken either within the course or from one of the robots. But you can see this is the robot having to navigate through a narrow hallway and doorway, through water. It's taking the drone in there so that it can be launched. There's the launch of the Emerson drone. And coming up, you see something that no other team managed to achieve, and that was successfully having the drone enter a shaft and actually explore the shaft and successfully manage to leave the shaft. Some of the teams managed to get their drones down the shaft, but not actually retrieve them, unfortunately. So again, Australia performed really well in this challenge, and although in this challenge, in the first challenge, the team came 5th, in the second challenge, the team came 4th. We're yet to find out the results of the next challenge. But what the team did beat all of the other teams in was in the accuracy of their positioning system. And this is a colorized map that has been produced that shows you, I guess, what the robot is seeing. And I guess this is a rendered version of the course that they were competing on for that second challenge using Paint Cloud. And you can see the level of detail and accuracy that we're now able to achieve by this Australian developed technology. And it's going to have a lot of applications in the underground mine space, but you can see they were able to build up a comprehensive map of all of the areas where the robots were able to navigate. So the point of me showing you some of these examples and the trends and where things are happening and where things are heading in cyber physical systems and where they might be applied in the mining sector is really just to underscore the need for us to be developing our own sovereign capability in this area. I think if COVID has taught us anything is that, you know, the supply chain model breaks down in the event of things like a pandemic. And so people have had to work remotely. We've had to use a lot of digital online tools and remote services. There's been a huge demand for robotics and AI related technologies, and yet with the disruption in our supply chain, it also can be very hard for us to get access to those technologies. So I think it would be better for everybody if we were creating more of these technologies right here in Australia. So I'll leave it there. Thank you.
Sue, thank you very much for a very interesting presentation and one that's kind of highlights the level of capability that's been developed in Australia. I think that you and I have had this conversation a number of times, and it's been highlighted across some of the other conversations in the last 2 days, the need for speed in innovation. In other words, leveraging the capability that's available now. So in areas we're developing very, very powerful capability, but the need for collaboration in that the companies that are close to the customer, the clients, that the companies that actually can see the problem, to rapidly engage and collaborate with the companies that have the technology to be able to accelerate the solution. You don't have to be a robot expert tomorrow, but you can leverage the robot expertise available in Australia to accelerate solutions. Is that the way you see it?
Yeah, I think that unfortunately some of our technology is a well-kept secret, and that people, you know, don't necessarily look within Australia to find solutions. And I think that's something that we have to change. It is true that the industry is fragmented, and we can be doing a much better job of letting people know what those capabilities are. And I think, yeah, it just requires a bit more boldness too on the part of the people developing these technologies to take a chance and actually look to become world leaders in some of these areas.
So the cluster that's emerging in Queensland, obviously that's one way of creating aggregation, and at least if you are interested in leveraging that capability, you can reach out to Queensland. How many companies are participating in that cluster?
I look more after the national side of things. Andrew Scott is the director for the Queensland Robotics Cluster, but I'm pretty sure he's got more than 100 robotics companies on the list there. And Paul Lucy has been doing a good job working in with Mets Ignited on a West Australian cluster as well. I'm not sure how many potential member companies there are there, but I think that this is, I guess, where we're evolving. So starting to get better organised, put people in touch with one another, develop these clusters so that we can really start to harness the talent that we have in these areas and encourage investment so that we can grow.
Excellent. And of course, we got the NeroVab facility that we've secured here in WA, so that'll be pretty exciting. Sue, thank you very much for your time, as always, and thank you for sharing where the robotics sector is today here in Australia.
Thank you.
So we move on. That was, again, another great presentation. I think the work that Adrian Beard presented from the Mets United side and the work that Sue presented shows an ecosystem in Australia that's accelerating and an ecosystem that's active. And putting those two things together, the concept of you don't have to do it all yourself, but being able to collaborate such that you create an innovation that will move the needle is where we need to be heading. And I think Australia is well placed to be able to continue to take an enormous lead in that sector. So we're coming to the next roundtable, which will be at the next roundtable, which will be at 1:10. This roundtable will be chaired by Peter Sherwin. And the roundtable focus is understanding the skills required to deploy autonomous systems and to support decision making in this autonomous world. Peter is, in actual fact, a transformation consultant for the mining automation sector in Australia. She is, in actual fact, developing the programs for training in WA, and I think you'll find her insights really valuable. I encourage you to join the roundtable. It starts at 1:10 p.m. Western Australian Standard Time, and upon completion of that, we'll have a break, and we'll see you all back at 2:10 this afternoon for a presentation from Adam Seidman, the acting deputy head of the Australian Space Agency, and we will be concluding the conference with Miranda Taylor's presentation, the CEO of NERA, where she will be talking about the challenges and opportunities for moving towards a low carbon, sustainable and circular economy. So please join Peter in the roundtable, and we'll see you back at 2:10. Thank you.